In this episode, we focus on designing secure remote and site connectivity using virtual private networks, VPN, and Internet Protocol Security, IPsec, but with a specific architectural goal in mind, preserving identity, integrity, and scale at the same time. Beginners often hear VPN and think it simply means a private tunnel that makes things safe, but a tunnel alone does not guarantee you know who is inside it, whether data can be trusted, or whether the design will still work when thousands of users and devices need access. Security architecture is about making those properties explicit and durable, not assumed. Identity means you can reliably know which user, device, or service is connecting and what they are authorized to access. Integrity means you can trust that the traffic has not been altered and that the connection has not been hijacked or manipulated. Scale means the solution can handle growth in users, devices, sites, and services without becoming so complex or slow that people bypass it. The goal is to understand what VPN and IPsec provide at a high level, how architects choose strategies, and how to avoid fragile designs that collapse under real-world use. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A good starting point is to define what a VPN is in plain terms, because the term is used broadly. A VPN is a secure communication method that creates an encrypted and authenticated connection over an untrusted network, typically the internet, so that traffic can travel as if it were on a trusted private path. VPNs are used for remote users connecting to internal resources and for connecting entire sites together, like linking a branch office to a main office. IPsec is a suite of protocols used to secure IP traffic, and it is often used to build VPNs, especially for site-to-site connections, although VPNs can also be built with other technologies. The key point for beginners is that these are mechanisms, not complete security solutions. They protect traffic in transit and can enforce authentication, but they do not automatically decide what access should be granted once the tunnel exists. They also do not automatically prevent compromised devices from using the tunnel. Architecture must therefore decide how to bind identity to the connection, how to enforce authorization, and how to ensure the tunnel does not become a hidden trust path into sensitive networks. Identity preservation begins with understanding that a tunnel is not the same as an identity, because the tunnel is a connection, while identity is who or what is using that connection. If a VPN is authenticated only with a shared secret that many users share, then you lose individual identity, which makes accountability and revocation difficult. If a device can connect without proving its own identity, then a stolen credential might be enough for an attacker to enter. Strong identity preservation usually requires unique authentication per user or per device and a way to verify that identity is legitimate and current. It also requires a plan for revocation, meaning if a user leaves or a device is compromised, access can be removed quickly. Architects also consider device posture, which is the idea that identity may include not only who the user is, but whether the device meets certain expectations, such as being managed and up to date. Even without discussing tools, the concept is that access should be tied to verifiable identities, not simply to knowing a password. A scalable VPN design treats identity as a core requirement, not an optional feature. Integrity preservation is about making sure traffic is not modified in transit and that endpoints are actually communicating with the intended counterpart. Encryption provides confidentiality, but integrity requires mechanisms that detect tampering and reject altered traffic. IPsec includes integrity protection as part of its secure communication approach, ensuring packets cannot be changed without detection. Integrity also includes protection against impersonation, where an attacker pretends to be a trusted endpoint, which is why mutual authentication is important in many designs. For site-to-site VPNs, integrity often depends on the gateways correctly authenticating each other and securely negotiating keys. For remote access VPNs, integrity includes ensuring the remote endpoint is authenticated and the tunnel is not being intercepted or redirected. Architects also consider replay protection, which prevents captured traffic from being resent to cause unintended effects. The aim is to ensure the tunnel is not just private, but also trustworthy. A fragile design might encrypt traffic but allow weak authentication or skip validation, creating a tunnel that can be manipulated. Scale is a design challenge because VPN usage can grow quickly and brittle approaches break when they expand. A small organization might start with a simple remote access VPN for a handful of users, but later need to support many users, many devices, and many applications, often from many locations. If the design requires manual configuration for each user, each device, or each site, operational burden can become so high that the system becomes inconsistent and insecure. If the design routes all traffic through a single choke point, performance and availability can suffer, leading to outages and user frustration. Scale also includes policy scale, meaning the ability to express who should access what without creating a tangled mess of exceptions. An architecture that works for a single network may become unmanageable when there are multiple network segments, multiple environments, and different categories of users. This is where strategic choices matter, such as whether remote users should reach the entire internal network or only specific services. Designs that scale will tend to be explicit, segmented, and identity-driven rather than broad and location-based. One critical architectural decision is whether to use full tunnel or split tunnel approaches for remote access, and the security implications are closely tied to identity and integrity. A full tunnel design routes a user's traffic through the VPN, which can centralize monitoring and enforce consistent policy, but it can increase load on the VPN infrastructure and potentially affect performance. A split tunnel design sends only traffic destined for internal resources through the VPN, while other traffic goes directly to the internet, which can improve performance but can also increase risk if the endpoint becomes a bridge between internal networks and external threats. The key lesson is not that one is always better, but that each choice requires compensating controls and clear policy decisions. If split tunneling is used, the design must ensure the endpoint cannot be used as a pivot into internal resources, and monitoring must still provide enough visibility into relevant traffic. If full tunneling is used, the design must ensure the VPN capacity and redundancy can handle peak usage and failures. Architecture is about selecting trade-offs consciously, not stumbling into them. Another decision is the difference between remote access VPN and site-to-site VPN, because they have different identity and scale considerations. Remote access VPNs connect individual users and devices, so identity management is central, and scaling means handling many concurrent connections with strong authentication. Site-to-site VPNs connect networks, so the identity is often the gateway devices, and scaling means managing many tunnels, routes, and policies across sites. Site-to-site VPNs can create hidden trust paths if they effectively merge networks without segmentation, allowing broad access from one site into another. Remote access VPNs can create hidden trust paths if remote users are placed into highly trusted internal networks instead of being given limited, specific access. Architects mitigate these risks by placing VPN termination points in controlled zones, using segmentation to limit what the tunnel can reach, and applying policy based on identity or site role. The tunnel is a transport mechanism, but the network placement and policy determine the real security outcome. A secure strategy makes the tunnel an intentional path, not a universal bridge. Key management and negotiation are crucial for integrity and confidentiality, and they also influence scale because poor key practices can lead to operational instability. IPsec relies on negotiation processes that establish shared keys for encryption and integrity, and those keys must be refreshed periodically to reduce risk. If key lifetimes are too long, compromise has more impact. But if lifetimes are too short without planning, renegotiation can cause performance issues or connection drops. Architects look for stable, well-supported negotiation settings that balance security and reliability. They also ensure that certificate or credential life cycles are managed, because expired certificates can cause outages that pressure teams to weaken security. This connects directly to the idea of preserving identity, because certificates often tie identities to keys, and identity systems must support issuance, renewal, and revocation. A fragile VPN design is one that works until the first certificate expiration event, at which point teams scramble and may bypass validation to restore connectivity. Durable designs treat lifecycle events as expected and plan for them. Segmentation is a recurring theme because VPNs are often used to cross trust boundaries, and crossing boundaries without segmentation can expand attack surface dramatically. When a remote user connects, the VPN should not automatically grant access to every internal system, especially sensitive services or management interfaces. Instead, the strategy should define which user groups can reach which resources, and it should align access with the principle of least privilege. For site-to-site connections, segmentation matters because different sites may have different security postures, and compromise of one site should not automatically grant access to everything at another site. Architects often define zones and policies such that VPN traffic is treated as coming from a specific trust level, not automatically trusted because it is encrypted. This is important. Encryption is not trust, it is protection during transit. Trust decisions are made through identity and authorization policy. When VPNs are combined with segmentation and clear policy, they support controlled connectivity without creating an overly flat network. Availability and resilience are part of scale, and they matter because VPNs often become critical for daily operations. If remote access depends on a single VPN gateway, and that gateway fails, users can be locked out of work. If site-to-site connectivity relies on a single tunnel and it goes down, critical services might break across locations. Architects therefore design redundancy, such as multiple gateways, diverse paths, and failover strategies that keep connectivity stable. They also plan capacity so that peak usage does not cause slowdowns or drop connections, which can lead users to seek insecure alternatives. Monitoring is essential here because you need to see connection health, authentication failures, unusual traffic patterns, and policy changes that could indicate attack or misconfiguration. The objective is to make the secure path the reliable path, because reliability reduces the pressure to bypass security. A VPN strategy that is secure but unreliable will eventually be worked around. A VPN strategy that is secure and reliable can become a stable foundation. When you bring these ideas together, designing VPN and IPsec strategies that preserve identity, integrity, and scale means treating the tunnel as only one component of a larger access and trust architecture. Identity must be strong, unique, and revocable, so you always know who or what is connecting and can remove access quickly when needed. Integrity must be enforced through authenticated negotiation, tamper detection, and proper endpoint validation, so traffic can be trusted and not easily manipulated. Scale must be addressed through segmentation, policy design, operational lifecycle planning, and resilient infrastructure, so the solution remains usable and maintainable as the environment grows. The best strategies avoid turning VPNs into universal bridges and instead make them controlled, intentional pathways that support business needs while limiting risk. If you can clearly explain where VPN connections terminate, what they are allowed to reach, how identities are validated, and how the system stays reliable under growth, you have an architecture that preserves the properties the title highlights. That is what makes VPN and IPsec a durable part of security architecture rather than a fragile patch.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.